Okay, I want to tell you how you use Gauss's law to solve for the electric field in a non-uniform spherical charge distribution. Okay, so what is a non-uniform spherical charge distribution? What is that? Okay, well, it's kind of like this. It's notice the shading in this sphere. This is a sphere, and this sphere the charge isn't uniformly spread out. The charge, as you get further and further away, the charge gets greater and greater. So it's not shaded too much in the center, but as you go out, the charge density, the amount of charge per volume, gets greater and greater. And so we say that rho is not a constant anymore, but it's a function of r. It's a constant b times r. Now, if you look at this, what it's saying then is that when you're at the center of this sphere, there isn't any charge density at all. Okay, so first let's find out what is the total charge of the sphere. Okay, if we know this to be the case, and we know that this is a capital R for the radius of the entire thing, then how much total charge is enclosed? Well, one thing for sure, I can't just multiply, I can't just do this. The total charge enclosed is not, I can't say it's Q is equal to rho times the volume, and then go, the rho would be beta capital R for the whole thing times the volume 4/3 pi r cubed. I can't do that because then that's exactly what you would get if the charge density were not varying, but it was consistently this value, b times capital R. So if it were, you see how dark it is here? If it were that dark throughout the entire sphere, then that's what you would get. It'd be just b times r times 4/3 pi r cubed. See, the math, you're not telling the math at all here that the charge density actually varies. Okay, so how do you do this? Well, let me tell you what you do. What we're going to do is we're going to take a very tiny, a very thin shell. You see that shell? I'm going to make it very thin, and that's a spherical shell. Now that very thin shell, it has a thickness. Let me put that shell here. So we can talk about it a little bit. It's very thin. That dimension right there is dr thin. It's really, really tiny thin. And I'm only talking about that right there. There's a shell. It's a hollow shell. And it turns out that the charge enclosed in that hollow shell is going to be dq. And it's dq because even though that's a lowercase r, dr is so small that it's infinitesimally thin, so that you hardly get any charge enclosed in there because it's so small. But the charge enclosed will be whatever rho is at that point, whatever the rho is, the charge density, times the volume of that shell. So the charge enclosed by the shell, that's dq, is equal to the rho there times the volume. Now, what is the volume of a shell? What it is it's the surface area of a sphere times the little height dr. And so that's going to be the surface area of a sphere is 4 pi r squared, and then times the surface area, the thickness of that, so dr. Okay, so one more time. This is super duper important here. What I'm doing is I'm finding the charge enclosed. This is my game plan. I'm going to find the charge enclosed in this little volume. And when I figure out an expression for that, then I'm going to sum them up with an integral and get the total charge enclosed. So the charge enclosed by the shell, so dq of the shell, is equal to rho right at that location times 4 pi r squared dr. This is a little volume dv. In fact, we can say that dq is equal to rho dv. Or another way of saying it is rho is equal to dq over dv. Okay, well, in any case, let me find the amount of charge that's in just this shell. It would be this. The amount of charge in that shell, dq, is equal to what the rho is there. So rather than, well, let me write this over. It's rho times the little volume of the shell, which is 4 pi r squared dr. Okay, so, but for rho, that's br. So I'm going to replace that. Rho is br. That's rho. And then this is the little volume, 4 pi r squared dr. That's the little volume. All right, well, I don't want just the charge in that shell. I want the total charge. So the total charge will be summing up all these shells. And so that's going to be b times 4 pi, and I'll bring these r's together, r cubed dr. And I'm going to tell the integral to start adding these shells at r equals 0. And don't stop adding them until you get to r equals capital R. So how much charge is enclosed? The total charge enclosed is going to be, I just got to take this integral. So pull the b, the 4 pi, out. And when I take this integral, I get 1/4 r to the 4th power. And I'm going to bring a 0 here and the r over here. Now when I put in those values, when I put in the r, I'm going to get b pi all over r to the times r to the 4th. The 4's cancel. And then minus 0. Does that work out? Yeah, that works out. So what is the total charge enclosed? b pi r to the 4th. That's the total charge enclosed. Let me just say, I have 2 minutes. Let me just explain. Probably the thing that maybe you don't get is, why is this dV? Why is that dV? So let me just finish up by saying, hey, if I had a very thin coin, let me start, let me even go one further back. If I had a very thin piece of paper, it was so thin that this distance was dy, and let's say we had an x and a y. This distance was x, and this distance was z. Then the volume of this paper is very tiny because the dy is so little. It would be x z times dy. Same with this. If this were a coin that had a radius r, but it was infinitesimally thin, we'll call that dy. What is the volume of this coin? If this is infinitesimally thin, the volume is going to be dV, because it's going to be really tiny. And so that's going to be the surface area, pi r squared, times dy. So it's just this times the height, dy. All right, well, same thing with a sphere. A sphere If you want to get the volume, it's the area times dr.